Was ready. Okay. Good afternoon, everyone. Welcome to the College of Optical Sciences Colloquium series. You probably know the majority of our students, would go to industries right after getting a degree here. So that is why I thought, it would be great to have somebody from the industry to come to give a talk. So here you are. It's my great honor to introduce Dr. Shibin, who is president and founder of Add Value Photonics. So his company is located in the Optics Valley. So you know where it is, right? He's running a company with 25 employees now, and he told me that he's near the airport, right? So you know where he's at. So before founded Add Value Photonics in 2007. He served as the Chief Technology Officer and co-founder of NP Photonics, right? So you guys have heard about that company, I hope. So his research covers fiber laser, fiber amplifiers, and photonic devices using non-silica glasses and fibers. So he has authored more than 150 publications, edited 18 preceding books, and he's awarded 39 U.S. patents. So that's a significant number of patents there. He is also the recipient of the Guattari Prize in 2005 from the International Commission on Glass, the 2012 R&D 100 Award, and 2014 R&D 100 Award. So he has served as General Chair, Program Chair for 23 technical conferences. He is also the Fellow of SPIE, Fellow of OSA, and the best thing, he's also an adjunct research professor here at our college. So let's join me to welcome him. Thank you for coming.
Thank you, Con. Thanks for the nice introduction. For me, I'm very glad to have the opportunity to come back to here to share with you what we have been working on at Add Value Photonics in the last several years about fiber lasers and components using specialty glasses. I'm going to start with very simple cartoons, or also a simple layout of solid-state laser and the fiber laser. Here is solid-state laser with laser crystal and two millers to form the laser cavity, and here's a pump. Here is simple layout of fiber lasers. Here's some pump, grating, and fibers, GaN fiber, or sometimes here GaN fiber again, or deliver fibers, but everything fused spliced together. So one thing I would like to emphasize is for the solid-state laser, now you have cavity, you have crystal, you have pump. A lot of laser design got to be involved. How to generate, for example, good mode quality or whatever. And even the pump overlap with the signals, and a lot of design to be involved. But for the fiber lasers, once you fin splice it, you cannot do too much anymore. Okay, you buy the pump, buy the grating, buy the fibers. You pretty much buy everything and fuse them together, and that's it. So from technical point of view, fiber laser is truly very simple. Once you get there, you basically do not need too much design, right? But fiber laser, because the fiber form and especially fiber laser is very easy to be amplified, and you have seed laser and first stage amplifying and second stage or power amplifier, whatever. You can add more, and as long as you have effective oscillator here, you can block lasing. Then you just can add amplify there. And for such kind of fibers like that, typically it's double cladding fibers, very simple double cladding fibers. And the core has very highest index. Then here's inner cladding, then outer cladding, and basically it's now the pump is multi-mode area, and a signal is a single mode area. So basically it's excellent pump kind of mode polarities converter. Okay, and all of us basically always work here try to increase the brightness of the laser. And the fiber laser truly offer you kind of very simple, reliable approach. In fact, is generative, basically offer such kind of approach to, to achieve what you want. And for the fiber lasers, since now everything fin spliced together, which means they are very reliable, right? What can you do with that? either break it or works very well. So very, very reliable. And because fibers itself is very small, so which means now you can effectively cool the fiber very efficiently. Now, for the lasers, when you can cool efficiently, most of the time the efficiency also could be very high, could be improved, right? And also for the pump, for such kind of laser, typically, for example, like ytterbium 1 micron lasers, the pump laser is like near the XX dot lasers, wavelengths very close, and confinement very well because pump can be confined in the cladding of the fiber, which means can propagate very long distance, okay, meters distance with very low loss. When very low loss, which means now pump efficiency could be very high, then overall the laser efficiency could be very high. So from this point of view, in fact, it's, fiber lasers truly has many advantages, and especially in the, the practical application area. But I keep telling people, in fact, fiber laser from many point of view, or especially from scientific point of view, it's very simple. And because, the fiber is very small, so it's compact, it's not complicated, so, it's compact. And the design is very simple, I just show you. You see, it's fusing, spice them together, and very simple. And manufacturing process-wise, compared to solid-state laser, it's very simple as well, at least if compared to solid-state laser. And here's I took the picture of the quant company, K Photonics. This monolock laser, I try to prove my point here. Okay, this monolock laser, and as all of you know, to build a monolock laser is not easy, right? But he can build a monolock laser this size. Here's a key, which means it's truly very compact, right? And he can ship it, and at least he will tell you it's very reliable, right? So it's reliable. And very importantly, I do believe Quantum Power is assembled the laser by himself. Okay? Assembled by. And tell me, think about what kind of other lasers professor can assemble and to ship it to the customer. Probably this is one of the very few lasers you can do. So which means from manufacturing point of view, it's truly kind of could be simple. I'm not saying it's very easy, but it's compared to other monolock laser. I don't believe any professor want to assemble monolock laser to ship it to the customer, right? Because problems going to happen. So which means from their point of view, it's truly, it's a simple manufacturing process. But thing is, because look like very simple, at the same time, you cannot adjust it too much, right? So which means now all the burden you shift to the engineering work. Because from design point of view, it's very easy to understand, or relatively easy to understand, but a lot of engineering work. So lots of engineering work need to be done. And most of scientists or engineers don't like to do it because it's very tedious. Because sometimes fiber just, boom, broke. You do not know what's happened. And there's no theory to tell you what's happened. But it happened. And it's a lot of work. But same time, so industrial people, especially in the application area, manufacturing industrial engineers, they love such kind of laser. Because now, and they don't have to worry about the laser too much because there's no button you can need to adjust. So which means either works very well or broken. If broken, just ship back to the manufacturer, right? Because he cannot do anything. So industrial people, they like laser like this because it works well or does not work, right? And so in the last 10 years, fiber laser, from the business point of view, truly doing very well. So one of the way to verify, for the companies, for the products, how the product doing, and basically is, one good way is to check the stock situation of the company who are making the products, right? Here's, the Spectrophysics in Newport, and, Newport Spectrophysics is one of the oldest laser company, and they're doing very well, and, here's the, price earning ratio is 22. It's pretty good because compared to typically it's only 15 or 17, so they're doing very well. Coherent even doing better. Coherent even doing better, and their market cap is like $1.6 billion, and PE ratio is about 25. But if you look at other company, one of the RPG, everything focus on fiber laser. Okay, focus on fiber laser. Now the market cap is $4.8 billion, and by the way, this one is not bubble because their PE ratio is not too high, which means they're truly shipping stuff, right? And so which means a real business. And RPG is founded by Dr. Gapontsev, in fact, in the 1990s, in the one of the institutes in Russia. And most of you probably know he founded the company during that time is because former Soviet Union is falling apart. They are looking for money to support themselves. So engineers, scientists try to support themselves. So basically, with such kind of pressure, he started his company in the basement. In 1990, and he started making the laser, well, like shipping more in terms of volume-wise. It's like about 10 years ago, because I was told 2005, and it's RPG basically is some company RPG is basically is on the market for sale, and their asking price is $100 million, but nobody wants to take it. So what I'm trying to say is, from 10 years ago, $100 million, nobody wants to take it. The company now it's $4.8 billion. So, which means business-wise, it's truly doing very well. And in fact, it's now, I was told 2014, more than 50,000 units of laser shipped to the manufacturing industries, or 50,000 units. And it's still growing with a 20 or 25% annual rate. So which means after 12 or 15 years, we will see like 1 million units of laser will be in the manufacturing factories. So which means it's tremendous, right? So which means also it's good for all of us, because now laser is not a toy in the lab anymore. Because think about 1 million laser in the manufacturing floor, it's a lot of lasers, right? But when you look at these lasers, I mentioned to build a fiber laser is very simple, right? But when you look at how generated laser or amplified laser, even simpler. So because the host that they use is just a silica, okay, SL2. SL2 is for the people not in the material science. I'm surprised to see group of material science from France here show up. Otherwise, I thought I was the only person know glass, but now I cannot see, can claim that, because they have 5 professors from France there here in the material science area. So for the people who do not know, silica, it's just a sand. It's just very pure sand. Okay, so material self, it's very simple, extremely simple, and the glass structure point of view, it's like silicon, oxygen, tetrahedral, and especially for SiO2, and it's just like one tetrahedral connect with another 4 tetrahedral, and just very simple glass structure. And the thing is for us, for like me, by training is the glass person, we don't like that idea, because for now the only professors who like to win Nobel Prize work on silica, because amorphous structure is a very challenging topic, and they try to figure out what amorphous mean, right? Amorphous mean. But for the normal glass scientists, we don't work with silica anymore. We want to work with other group of glasses, because from glass point of view, and from glass point of view, even for oxide glass, there's many other glass there. Most of us working on other glass. Okay, only very few people working on silica. And from scientific point of view, now even less, because as I said, it's only people working on the structure, not how to make silica. They're working on study SiO2, because it's so simple. But now for us, we work on all these glasses, and which means what can we do, right? So we have to, and we also typically scientists are very good. We invent something for us to do. It's basically sometimes not needed, but but we try to, we always try to do something. And also another challenging thing is for the fiber laser community, because silica is so popular, and they only use there are 2 types of glass. One is silica, and another is everything they call soft glass. Soft glass. Everything else they call soft glass, right? So I use a similar slide like this one multiple times now, especially at the SPIE, the meetings like that. Try to tell people, hey, non-silica glass is not soft, because somehow they just only 2 types of glass. One is silica and other soft glass, because I think it's here it's a glass bridge in Grand Canyon, and this one in fact built with silicate glass, not silica. And everyone believes now the iPhone glass definitely is not soft, but because but this one is not silica; it's a silicate glass. Okay, silicate glass. So in fact, it's for us, most glass scientists are working on non-silica glass. That's what I'm trying to say. But when you look at the silica glass structure point of view, as I mentioned, silica, oxygen, tetrahedron, and connect with another 4 tetrahedron. So structure-wise, it's very, very simple, right? Very, very simple. But there's one issue there. Because the structure is so simple. Now, for the low Earth, especially for laser application, for some application, also, particularly for like pulse laser, you always want to have high low Earth doping concentrations. But now the silica is very, very difficult to put in there because, the structure-wise is very limited. And once the doping concentration increase, some of the so-called like bridging oxygen broken. If in the glass sense we call the bridging oxygen because the bridge to the silica. If the other one is kind of broken, then which means now some area is open. Then if we want to put high low Earth into the host, all low Earth will try to stay together. Just one local area. When they stay together, then the problem comes out is the so-called ion cluster. And ion cluster is, which means, basically is all ions stay together. When they're excited, they work together, produce another photon with a high energy. And which means now this wavelength is now you want, and same time, basically the energy disappear, right? Because, so it become loss. So for the typical silica fibers, and the doping is limited, then gain per unit length is limited, then, so basically always need a few meter long fiber to generate the laser, but then sometimes optical nonlinearity is issue. Right? Because especially now for the high pulse energy, optical nonlinearity issue. But for the glass, in fact, if you look at it from structure point of view, for example, in the silica, if we introduce sodium into there, then suddenly, structure changes dramatically. And the so-called, the bridging oxygen, then separate. Now here's the sodium. Now you see a lot of wide area, and basically layers can stay inside. Okay. Not only have site here, you will see all these sites, they are not connected, which means if we engineer the glass composition very well, we can dope high low Earth into the uniformly. And uniform because, as I said, if you in the silica, if you put low Earth there, they will stay together to form so-called cluster. But here, if we engineer glass composition well, then we stay uniformly. Now we can have very high doping concentration. When high doping concentration, which means we can get high gain per unit length, which means now fiber could be shorter. When the fiber is shorter, then we can produce high peak power lasers, and which could be quite useful for for many applications. So for this glass, this type of glass we call the so-called multi-compound glass, and since oxide base we call multi-compound oxide glass, and the glass former could be SiO2, which is called silicate glass, and P2O5 is a phosphate glass, so different kind of glass. Here's germanate or borate, and then with different other elements. I'm not getting into the the detail. And compared to the silicate glass, because as I mentioned, its glass forming area could be much bigger now because you can work with all with produce different kind of glass composition. And from laser point of view, more important now is a lower solubility can be higher, then you can dope with high doping concentration, as already mentioned. And also now you can engineer the photon energy of the material as well, because some of the phosphate glass, phosphate has it's a high photon energy, and germanate because GE is much bigger than Si silicon, which means now the photon energy is it's lower, so it could be useful for some of the laser, long wavelength laser, because long wavelength laser always prefer low photon energy, because then multi-photon the loss will be lower, and also can improve the so-called photo darkening issue, because for the silica fiber it's always has photo darkening issue. And when I was here, I left here in 2001, so it's about 14 years ago. I guess time flies. But anyway, when I was here, I was mainly working on phosphate glass. Okay, mainly working on phosphate glass. So for the other one, phosphate glass, phosphate is 5+. So which means now with 4 oxygen come together, so one oxygen always has so-called non-bridging oxygen. Okay, these 2 oxygen connect with 2 phosphates, but this one is always kind of non-bridging oxygen, which means phosphates by nature itself, in fact, is structure-wise could be like a different kind of structure, and they are not so well connected, which means now the doping concentration could be high. So at that time, we dope very highly with like ytterbium doping concentration and erbium concentration. We mainly try to optimize so-called conversion coefficient. After optimize this one, which means now erbium doping concentration can be higher. So we, in fact, we reduce this factor by with this one by factor almost 10, which means now we can put very high erbium into there. I'm not getting into the detail because quite old data anyway. So at that time we demonstrate the very high, because we could have a high doping concentration, which means we could have a high gain, and per unit length we demonstrate 30 dB per centimeter gain, and also like 5 dB per centimeter gain. And in fact, all this is done by the student here, when I was here. And since the fiber could have such a high gain per unit length, now we can use such kind of fiber, fusion spice with the two gratings to form the simple linear cavity. When such kind of linear cavity formed, when oscillating, the longitudinal mode depends on the length of the cavity, right? So because depends on the free spectrum range. When the cavity length is about 10 centimeter long, and I draw here, the line which means represent to each longitudinal mode. And for the gratings on the market now, you can buy, with bandwidth 0.07 nanometers. So now, if you get a grating like this, you buy it, and if the cavity length is 10 centimeter long, inside you will see a 7, 8 mode there. So which means 7 to 8 specific wavelengths inside the jump along. But now, if we shorten the cavity to 2 centimeter, now inside only one mode, which means now if we can temperature stabilize this cavity, then we can get single longitudinal mode laser. Now this is so-called single frequency fiber laser, and so that's that's what we were doing at MP Photonics, and that's what the core technology at MP Photonics. And so it's so-called single frequency single frequency fiber lasers, and plus is because here is narrowband is narrowband is and broadband, and because when you write gratings, in fact is on the broadband it's basically you have two polarization. You see two response peak, but if you match with the narrowband and the narrowband, then you just lasing at the one polarization. Now you can get just one polarization and single frequency. Fiber lasers and Linewidth could be very narrow, like kilohertz levels, which means the coherence length could be very long. And when I started new companies, then I tried to think about, okay, what other glass we can work on or should work on, right? So instead of phosphate glass, we shifted to so-called silicate glass. Okay, silicate glass. Here, the glass structure provides just like this, but for most of you, not too much meaningful. But I can, say silicate glass. In fact, you are very familiar with. In fact, all the window glass are silicate glass. All the most of optic glass, like BK7 glass, are silicate glass. So for the new company, we start to work with, just very similar to like BK7 glass. That's what we try to do. Okay, and first thing, because for such a glass, we can engineer glass composition to have a high doping concentrations, and then try to looking for new area to work on. So we start to focus on the 2 micron fiber lasers, and here is the simplified energy level of thulium ion. Thulium ion is most popular ion for the 2 micron laser generation. Here in fact, Leon Eastwood group at the Naval Research Lab in the end of the 80s, they found for the thulium YAG, for the when the thulium doping concentration increased and quantum efficiency could be increased to almost 200%. And the reason for that is when you excite the thulium from SuliH6 level to the SuliH4 level, and now there's another transition from SuliH4 level to this level and SuliH4 level, but SuliH4 level is the lasing level. Okay. Here's a laser transition. But from the SuliH4 level to, from SuliH4 F4 level for this transition, so the wavelength, in terms of wavelength-wise, is 1.5 micron, close to 1.5 micron. And which means energy-wise is enough to excite another, ion from ground state to excited state. So what happened is now, when the thulium doping concentration is very high, especially the thulium, they stay together. When you excited, the thulium with one high energy photon, here is near 0.8 micron, excite to here, and when it drops from here to here, can excite one neighboring ion to the excited state. So now one pumping photon can produce two laser photons. That's why I say, they said quantum efficiency is 200%, but energy efficiency is still less than 100%. Okay, because 0.8 and has 1.9, so if two photons, the wavelength is 1.6. So 1.6, 1.9, so the energy efficiency still less than 100%, but the quantum efficiency could be 200%. And so we try to use, such kind of, silicate glass. These ones are similar. So anyway, we believe, we submit a proposal to, Air Force Research Lab, told them, hey, we believe this one is the best host for the 2 micron laser generation, and they start to give us money. So that's how we start the company. And so we make the glass by ourselves. Start from chemicals. We put very simple ovens, and to put inside. Then we make the glass by ourselves. And here, just show you so thulium doped glass with different doping concentration. Here, it's from 2% to 6%. Here, it's from 4% to 12%. Here, so this doping concentration. I just want to show you we can dope at any this level. Just want to show you, okay, what kind of doping level we can do. Okay. Then we may direct measure the emission spectrum. Okay. You will see that for the 2% example. Okay. By the way, from laser point of view, 2% already very high, because in silica typically they work with 0.2% or maximum 0.5%. Most of the time 0.2%. So 2% is already very high, especially compared to somehow like erbium doped silica fiber like that. You will see emission, a little bit emission. I just mentioned, one emission transition wavelength was near 1.5 micron, right? 1.5 micron. But when the doping concentration increase, okay, this peak dropped dramatically, almost disappeared. So which means from energy, here's a simplified energy level of the thulium. So when there's doping concentration is low, when there's no so-called cross-relaxation energy transfer, when you excite it, then the emission-wise you will see near 800 micro emission, near 1.5 micro emission, then mainly is near the peak-wise 1.8 micro emissions is for the 2 micron, near 2 micron laser generation, right? You will see that. But when the cross-relaxation energy transfer happen, and as I mentioned, this one will disappear because when this energy when this one drop to here, it will transfer energy to the neighboring ion, which means another one will be excited to this level. So that's why when you measure emission spectrum, 1.5 micron emission can disappear because transfer energy to the neighboring ion. So and then as a result, and near to 2 micron or 1.8 micron emission can enhance. Okay, so I just show you. So these direct emission measurement results, which means in our glass, such kind of the so-called cross-relaxation is happening. Right? But this is purely still from spectroscopic point of view, right? Very important is from laser point of view to verify. That's more direct, right? So to verify. So which means now we got to make it fibers. So we use so-called rod-in-tube technique to make the fiber. We make it glass, and then make a rod. Rod is the core glass. And then we make a tube. When we put a rod in the tube, then we draw the fiber. Okay, draw the fiber. And then once we have the fiber, then we test the performance of the fiber. And here is our test results, which were done quite many years ago. And the fiber is very simple. It's 20 centimeter long fiber, just not too long on this laser. And one thing is I said it's very simple because output is just it's like a it's cleaved end, and another end is dielectric coating. But one thing I want to mention is the efficiency here, slope efficiency is 68.3%, 68%. Okay, so pump wavelength near 800 nanometer. Lasing wavelength is near 1.95 micron. So if quantum efficiency is 100%, in fact, this slope efficiency only can be 42 or 43% if you go to calculate 1 photon to 1 photon. The slope efficiency only can be 40-some%. Now, in fact, the slope is 68%, which means truly so-called cross-relaxation is happening. And we estimate for this one is quantum efficiency is not like 200%, but it's about 180%. Okay, and we characterize some of one of the professors characterized some of the fibers. In fact, the gain per unit length could be quite high as well. The gain per unit length is more than 5 dB per centimeter, so very high. So since the gain is so high in terms of per unit length wise, which means now we can do the very similar things as we show you for 1.5 micron lasers, film splice with 2 gratings, and then to form very simple linear cavity to get single frequency laser. So we can get like single frequency 2 micron wavelength laser. And for the 1.55 micron is mainly for the sensing application. You might ask, hey, what's that for? For near 2 micron. In fact, 2 micron could be very useful for some application like even CO2 sensing. And I just show you one example. Here's a microstructure fiber. We filled fiber with CO2 gas. With the CO2 gas, then we we measure the basically measure the CO2 absorption. Use our laser. So with thermal tuning like that. And then so what I try to mention to you is single frequency near 2 micron laser could be quite useful for the CO2 detection. And we use also very relatively simple technique to build Q-switch laser by pressing the fiber. Basically, it's rely on the polarization. One end is PM, one end is non-PM. We just push the non-PM at one point. Polarization will match, then kind of achieve the Q-switch technique, and then we can get different kind of the Q-switch, and then we can amplify. Basically is single frequency Q-switch laser, and this is some data a couple of years ago, 2011. We published it at the Optics Letter, and at that time we achieved about about close to 2 kilowatts peak power, and sounds like not too much for for single frequency laser. In fact, the peak power not too high, but in fact, because the bandwidth is so narrow, when you launch into the fiber, in fact, even with just 300 watts peak power, if the fiber is a bit long, you will see kind of nonlinear phenomena, optical nonlinear phenomena. So, okay, so which means for us, in fact, I mentioned this one is try to mention to you, when peak power is high, we cannot use fiber as a deliver fiber. We have to use kind of at the end of fiber, we have to column it and then use free space. So 2011, we introduced such kind of Q-switch single frequency fiber lasers, and recently we try to push power to it's high pulse energy, and this one, in fact, I'll show you. We already introduce a product. I just want to show you some of data from the 1 units we delivered, and it's a single frequency 2 micron lasers, and the average power wise is 16 watts average power, and 50 kilohertz. So which means now pulse energy is more than about 300 microjoule. And for the people working in the area, well, know, okay, few hundred microjoule single frequency is a lot of pulse energy, because it's not easy to do. And it's we verify it's truly the single frequency. And for the such kind of amplifier, such kind of laser, one thing you have to make sure is there's no AAC there, because if AAC there, it's kind of cheating, because in reality, the pulse energy is not as what you claim, which means now, the AAC have to be well suppressed. And also because for such kind of pulse, people like to maintain megahertz linewidth for, for the like CO2 sensing like that. So the pulse width have to be long enough, because if the pulse width is shortened, then transform limit bandwidth will be much bigger, much wider now, which means now it's become no good anymore. It's for laser, in fact, it's for such kind of single frequency laser for us, okay, to build a 15 nanosecond laser is much easier than 150 nanosecond laser. Because 150 nanosecond laser, the bandwidth will be like 2 megahertz or shorter bandwidth. Now the SPS, stimulus boron scattering bandwidth, is also like tens of megahertz. So basically, you know, and the SPS, basically you have to kind of avoid SPS. And when the pulse becomes shorter, because transfer millimeter bandwidth become broader, sometimes even could be, you know, it could be a few hundred megahertz like that. So in fact, for single frequency laser, most people do not notice. In fact, hundreds nanosecond pulse is most difficult one to build. And also not only, you know, to build such kind of laser, also have to make sure the pulse is can look like nice shape, because for the fiber laser, when you amplify, if you do not manage it very well, and the front pulse will be very, very high, then because it takes most of the energy, and then the less the pulse just kind of, you know, almost in pedestal area. So you have to make sure, in fact, is, you know, the 30 dB bandwidth is kind of, it's broad enough. It's not like a whole bandwidth, which means now for such kind of, you know, laser, we have to do pulse shaping, which means at the very beginning, we have to make sure, you know, here's the front pulse, and front pulse, head front pulse have to be very small. Make sure small, so amplifying and following with the larger, you know, the intensities, and can form like a relatively nice looking pulse. And also, I like to briefly mention, you know, I mentioned, you know, we're working on 2 micron, you know, the Q-switch pulse laser. We're working on Erbium doped laser as well. We develop similar fibers with very high efficiency when we pump with near 1.5 micron in-band pump. And this one, we have a publication on that. And we're also working on 1 micron fiber laser as well. And for 1 micron fiber lasers, in fact, it's, you know, pulse energy could be much higher. And we can do up to, you know, 1 millijoule pulse energy. And in terms of average power wise, here demonstrate more than 100 watts. But it's a product we are promising to ship. Now it's 50 watts average power. I like to emphasize, okay, all these is single frequency fiber laser. Okay, it's not a, and for this one, fiber laser, in order to, you know, as mentioned, suppress the so-called SPS. SPS stands for stimulated boron scattering, and the fiber have to be short. Okay, core have to be big. That's why our high doping, high gain per unit length become very useful for such kind of application. And another thing I'd like to mention is when we use such kind of so-called Silicate glass host, okay, we can engineer the host to manipulate the bandwidth of the laser or emission. Okay, when we do that, for example, this one 2 micron, and you know the emission bandwidth. Now, if you measure ASC bandwidth, and our glass, one of the fiber we have, it's almost double than you know most of thulium-doped silica fiber. Okay, now which means more. This one such kind of broadband could be useful for Moloch laser. Right, so we work on quite a lot on the Moloch 2 micron fiber laser, because bandwidth is so broad, which means now we can achieve a short pulse. We started with very simple, you know, cavities. It's uses at the beginning we use like 30 centimeter long fiber, and do the Moloching, and then you know, to head our initial demonstration, and the bandwidth is, you know, 7 nanometers. And you might ask, hey, your spectrum is very broad. Why you here only get 7 nanometers? And in fact, for the Moloch lasers, you know, at the beginning I mentioned, you know, it's quantum laser. I said it's not easy to build Moloch laser, because Moloch laser now, especially the fiber laser, you have to engineer dispersion inside. And the big things now, and now you have to engineer the dispersion, or some many other things now become theoretically even not so easy anymore. And then we start to engineer dispersion inside the cavity. And then the pulse was for particular this demonstration now is shorter than 350 femtosecond, and we just keep going. And so now some of the bandwidth we demonstrate is about 50 nanometer bandwidth. Okay, we're still working on, and basically just try to you know, so go to even broader bandwidth. And since we're a commercial company, right? So for us, in fact, with the 50 nanometer bandwidth, if we use with good compressor, you can compress. If you know, you can compress to the whatever the pulse come out, we can compress to the you know, less than 100 femtosecond pulse width if we use good compressor. But since we're a commercial company, so we always try to use a bit more practical approach. So for this one, because we could deliver with the fiber, so we try to use fiber to compress it, just fiber itself to compress it with different lengths of SM28 fiber. In fact, and the shortest pulse we can compress to is about 140 femtosecond, and that's why, in fact, if you look at our website, we're claiming we can ship you the CD laser with 300 or 350 femtosecond, because we know we can use a fiber to compress, and this kind of a number we feel comfortable to make to build a daily base. So if you want to short pulse, we also can do that. And one thing very important is I'd like to particularly mention is we also started working on basically is build a gain fiber, try to manipulate the dispersion of the gain fiber, and because material dispersion is determined, but we try to to manipulate the waveguide dispersion, and you can see here the core become very, very small, index be very high, and so by using such kind of fiber, I think we can build some other kind of model lock laser with with a little bit unique features. We introduced this product in 2012, and so we're very happy. We we were awarded R&D 100 award, and so for some of you do not know, the R&D 100, it's so-called like an Oscar, for technology. So we feel not so difficult to get, but for the national labs, Department of Energy or the government labs, this seems very emphasized. They care about this award very, very much, very much. And so I mentioned to you, we have this such kind of the Moloch lasers, and recently we try to so basically is try to amplify to high pulse energy. For some application now, people always want to have like more than 10 microjoule energy. So in order to achieve like this, we have to stretch it, then do pulse picking, then amplify again, and then compress it. So we start to working on that, and we also start to offer product now, particular for example this one to one test data show you for for using our these fibers, and basically we can achieve 3.5 watts average power with 300 kilohertz, and which means now each pulse is about 35 microjoule, and so we always like to do that. Once we can do 35 microjoule, then we introduce products say 10 microjoule to make sure basically we can build all the time, because we have to make sure give us enough room, because make sure, because if a product yields low, the company will never be able to make money. So we always do not want to claim halo number in the product deliver sheet. And in addition to thulium, 2 micron laser, we're also working on the thulium, holmium core-doped. Okay, I'm going to briefly show you. And the very simple, in fact, it's thulium core-doped and thulium transfer energy to holmium, and holmium laser near 2 micron, but wavelength is longer. But when the 2.1 micron, then in fact, the transmission in air become much better. So many agencies like these wavelengths because the transmission is much better. And here is the different glass. You see color become heavier because the doping become higher, and here's different kind of glass absorption. I'm not going to go detailed. And here the typical output performance, laser performance of such kind of laser. And here's to set up for 2 micron Moloch is very similar to the one I just show you. And then here is the basically Moloch laser with demonstrate. So basically I show you it's we develop this such kind of glass. We demonstrate very efficient, and Q switch, Moloch, different ones, and single frequency, and more important is we commercialize these products. And now I'm trying to change a little bit subject, because in my title I also mentioned components, right? In fact, so I want to mention components, because one of the components we developed is so-called all-fiber oscillator. Okay, and all fiber. So here's the situation. So now we talk about fiber laser, right? So cedar, amplified, but in the middle there's always has oscillator there to make sure these two amplifiers are not connected. Because if they're connected, this one think about 20 dB gain, this one 20 dB gain, it becomes 40 dB gain. If another amplifier becomes 60 dB gain, then we're lasing like crazy, right? Because any wavelength, it can laser at any wavelength now. So I have to make sure I have the oscillator to block them. And but now, in fact, all these oscillator, okay, it's a free space fiber pigtail one on the market. Now the problem come out, in fact, is for now everyone knows when you try to launch, because now it's come from fiber, collimate to free space, and then go to the oscillator, and then collimate it back to the fiber again. Okay, so this collimation, when collimate back fiber again, it will be very challenging when the power is more than 20 watts. So that's why on the market now, whatever you can find, the maximum power is 50 watts, but in fact, all the manufacturers buy 50 watts, but the operating for the 10 watts for the manufacturers. Okay, for the lab you can do even 55 watts short term, but for the manufacturer always operate 10 watts because it's not reliable. Because think about now you need a couple laser back to single mode fiber with more than 10 watts. It's not reliable, right? Even worse, in fact, when backward power is more than 1 watt, okay, boom, it will damage it. I think anyone in the lab use it one, this is in fact is the problem. Okay, it's good to protect these amplifiers, whatever, if there's any backward lights, right? So now think about if any backward light here will be amplified. The small signal will be amplified, right? So very easy to exceed 1 watt. Then launching here and then they don't want damage it. So it's good to protect all these. But think about from industrial point of view, it's a laser broken, right? For the lab, it's okay. You can buy another one to replace it, right? And in fact, for more importantly, not fiber laser. People think about fiber laser for shooting down the missiles. You see publication everywhere. So, try to do beam combining to form the 100 kilowatts laser like that, right? But so you already have see demonstration for so shooting down the UAV like that. It's it's a open publication. I mean, you can find it from publication. So which means now you cannot handle backward power. So which means how can make a laser reliable? It's a very challenging issue. And this one is weakest point. So people in fact have been trying to work on this one for a long time, but just have no solution. And so we started working on this one about 5-6 years ago, and we use approach. So this so almost the same as the current Faraday oscillator, but we just use fiber-based. And we develop a fiber-based Faraday rotator and then finish pass with 2 fiber-based polarizer and form it. Okay, so it's principle. We never invented anything, and it's but we did develop both of these components, extremely challenging components, because many people want to try it, but they failed. And it's not easy to do, but we did. And since if we can do this one all fiber oscillator, now since everything fits best together, right? I show you everything. So which means it could be very reliable, right? And since also everything fits best together, which means it can handle high power, obviously, or at least relatively high, because you do not involve free space coupling anymore, right? And it's relatively simple, right? Relatively simple because everything you just fuse best together. And so the reason I would try to say it's not easy to do is because the Faraday rotation, typically the first pass you produce 45 degrees, right? When you come back another 45 degrees, then somehow the polarizer block it because 90 degrees. So you need a 45 degree rotation. And this simple equation governs the angle rotation of the polarization in the materials. And here's a very simple equation, the magnet, basically the Voigt constant of material, and here's the magnetic field flux density, here's the length of the materials. Okay, but the problem is when you in the Leo situation, when you calculate like this one, you will find that the magnet, especially permanent magnet, okay, you cannot just make it longer. In order to have large magnetic field, the diameter has to be bigger as well. So it has to calculate results. So which means now for if the V number is 10 radian per Tesla per meter, okay. So smallest the diameter will have to be 80 centimeter radius, okay. Radius have to be 80 centimeter, and the diameter is 16 centimeter. You see, length is 16 centimeter. So diameter and length have to become similar. It's the smallest point. Okay, smallest point. So which means now, if the material is 10 radian per Tesla per meter, so magnet have to be like this size. You could imagine pretty heavy one, right? So it's going to be heavy one in order to build such kind of all fiber based one. And for the free space laser, typical people use TGG. Okay, TGG is V number is 40. So the 40 is, which means now you can be somewhere here. So that's why in the lab you see the magnet diameter like this, because the TGG is, the radius, it's just only need, it's about 2 centimeters, something like that, right? But for the silica material, if we use silica, it's 1.1. Okay, if we use directly silica fiber, the magnet will be like 1 meter long, about 1 meter, about 85 centimeters long. So that Dr. Jerry Moore from S4 Research, in fact, he graduated from here quite many years ago because he already retired from Air Force Research Lab 2 years ago. He's the person getting me into this, and he came up with a very smart idea because he said otherwise need 1 meter diameter magnet, right? So it's almost talk about tons, not a kilogram. And he come up with so-called cross-surface match. So he used rather small mag one, then come rotating, and then basically he used multiple sections. So at the end, he showed me he built all fiber oscillator with 85 centimeter magnet, but like 24 piece or 25 piece, I forgot. The diameter like this one. So at the end, it's about 250 pounds, something like that. So still 250 pounds, but you can imagine Air Force or Department of Defense ask him to build one, and it's he has 2 patent, very innovative approach, which means that's truly needed. And also the risky part is magnet. In fact, put it together. If we can't find very well, it will fall apart. It will be very dangerous. And which means now for to achieve this, you have to have a material with a very high voltage constant. Okay, we develop fiber for this one, for example, is very close to TGG. Okay, very close to TGG, which means we can do relatively short magnet. So we make this glass and make a fiber and characterize the basically Faraday rotation. And so the Faraday rotation, then as I mentioned, to go back to V number very close to TGG. And so we develop this, all fiber oscillator. It's commercially available now, and that's, we are very happy. Last year we won this R&D 100 watt. So this pretty much, concludes my talk, but I'm going to briefly introduce, the company since we're in Tucson. And so, I officially left MP Photonics in 2007, but started working on this one in 2008. We're close to, near airport area. And for the moment, we have more than 10 PhD. We have 25 people. And we are building fiber lasers, but we start from chemicals. We build glass, build fiber, then we build the lasers. So we mainly focus on pulse laser, high peak power, high pulse energy lasers, which, from this aspect, we always can be better than RPG. There definitely we cannot, in terms of quality or products-wise, volume-wise, we cannot be as good as them. But in terms of pulse laser, we can do better. Sorry for the slides. And here, so basically we focus on industrial applications. So we have an application lab. So if someone you want to do laser material processing like that, you can come to our lab. We have a lab. We have all kinds of lasers there. And I like to emphasize, we basically try to use a specialty glass and the fiber, and then use this one as a core technology. But our product is lasers we try to sell. Okay. And for the moment, in fact, we need more help. We need more people, and we're recruiting 5 more people in the sales engineers, laser engineer area, and also laser technicians. Thank you very much for your attention.
Any question from the audience, Dimitri?